This is problem 36. An electron-positron pair can be produced by a gamma ray striking a stationary electron. So you start off with a gamma ray and an electron. Afterwards, you have an electron plus an electron-positron pair. Note that the charge is conserved in this situation. If the total energy is divided equally among the three end products, what is the initial gamma ray energy? I'm just going to make this line thicker so we can clearly see. This is before and this is after. So the total energy is divided among the three end products equally, and we want to find the initial gamma ray energy. So this is what we are looking for here. Assume the electrons and positron all travel along the line of the initial photon velocity, which means that all the y components for the momentum are 0. Okay, so let's first look at the rest energy. So the electron and the positron have the same rest energy, which is 0.511, and we will just call that E0 because in addition to the positrons and electrons we have a gamma ray, but the gamma ray does not have a rest energy. The gamma ray is a photon, and so the mass is 0, but we do know for the gamma ray that the total energy is equal to the momentum. So we have that. And this is for the electrons and the positrons. Okay, so we know that the total energy is divided equally among the three particles after the collision, but we don't know what the initial energy of the gamma ray is. We do know that initially the electron that we have is at rest, so that energy is just the rest energy. I know that these two quantities should be equal to each other, and since the electron is stationary, its initial momentum is 0, and so then let's consider the relationship between the energy of an electron or positron and its momentum. So we have the momentum for one of those particles would be, from this equation here, rearranged, would be equal to its total energy minus its rest energy squared, then take the square root, and we do not know what the total energy for an electron or positron is, but we do know that the rest energy is 0.511. However, we know that the three particles are going either in the positive x direction or the negative x direction. It is possible that this momentum is negative, so let's include the signs there. And we're going to have to consider what all the possibilities are in order to completely answer the question. Okay, so now for our conservation laws, we have to conserve energy and momentum. So for the gamma ray, we're going to call this E gamma plus 0.511. So here on the left-hand side of the equation, we have the total initial energy, And the total energy after the collision, because it's divided equally among all three particles, would just be 3 times the total energy for one of those particles. And we could rewrite this by bringing the 0.511 over to the other side. Okay, so now we have one equation from conserving energy, and now we will look at the conservation of momentum. So let's assume first that all three particles, so I'm just going to draw this for the particles after the collision. If all three are going in the same direction, then the momentum would be positive for all three particles. And my initial momentum is E gamma, because the momentum of the gamma ray is equal to its total energy. So I start off with E gamma, and then if the total energy is divided equally among the three end products and they have the same mass, then gamma must be the same for all three, which means the velocity is the same for all three, which means the momentum has the same magnitude for all three particles. So you could say this is 3 times the momentum for one particle, but we do want to use the equation here. So this would be 3 times the total energy for one particle squared minus 0.511 squared. And this, I'm going to rewrite. And this is going to be equation 2. But this is only for the case where all three particles are going in the same direction. So I don't think we need to use a computer for this one, but let's just take a look at what we have here. Okay, so I have E gamma here and E gamma here, so I can set these two equal to each other. So that gives me 3 times the total energy minus 0.511 is equal to 3 times the square root of this. And now we can square both sides. And this will be 9 times the total energy squared minus 6 times 0.511 times the total energy plus 0.511 squared. So that's what we had on the left hand side, and then here on the right hand side, that's just, this is 9 times 0.511 squared. Okay, then I have, oh, look at this. This and this cancel, so now it's not going to be too hard to finish this by hand. If I bring this over to the other side, it will be positive, so this is 6 times 0.511 times the total energy, and then if I bring this over to the other side, it would be plus 10 times 0.511 squared, and this is plus 0.511 squared, so this would be 10 times 0.511 squared. And so then the total energy for an electron or a positron after the collision is going to be 10 times 0.511 squared divided by 6 times 0.511 squared. And then we can say that this cancels with that. So that's going to be 10 times 0.511 divided by 6, which gives me 0.852 mega electron volts. So that goes here, 0.852, 0.852, 0.852. That actually might have been a mistake to put it up there because I still haven't checked the other possibilities and there might be other solutions, but I would want to add to the table. But let's just continue with all three going in the same direction. And I want to know the total energy for the gamma ray before the collision. Let's use equation 1 for this. So the total energy is equal to 3 times 0.852 minus 0.511, and that gives me 2.044. Oh, that is the answer. Well, it is an answer. So that would be 2.04. I'm going to box this, but remember we're not done because we still have to explore the other possibilities. And let's find the momentum, which comes from this equation here for the electrons and the positrons. So I have PCE is equal to, in this case it would be plus 0.852 squared minus 0.511 squared, and that gives me 0.681. And we'll put that in the table here also. Okay, now, is it possible that all three particles go in the negative x direction? No, that's not a possibility. So, well, I'm just going to write it up here because I'm kind of out of room. Okay, so can we have all three particles going this way afterwards? No. So the other possibilities would be to have one particle go backwards and two particles go forward, or you could possibly have two particles go backward and one particle going forward. And because the rest energy for all three end products are the same, it doesn't matter whether you say it's the positron going backward and the electrons going forward, or an electron going backward and the other two particles going forward. Okay, so because the rest energies are the same, that's not going to make a difference. So the equation 1 would stay the same. For equation 2, you would have E gamma, which is now the momentum for the gamma ray. Because the energy was split equally among the three particles, if you look at the equation that we have for the momentum of an electron or a positron here, the only thing that would change based on the direction is the sign. So the magnitude would be the same, but the sign would be different. So if one particle goes backward, if you add the momentum for this and this, they would cancel out, and that would leave you with the momentum for one particle going forward. So this would be square root of this. So instead of having a 3 here, you would have a 1 here. Then, for this situation, this one and this one would cancel, but now you're left with a total momentum in the negative direction Well, that can't work. So because the energy is split equally among the three particles, this is not a valid solution because you would end up with a total momentum in the negative direction, but your total momentum needs to be 2.04 in the positive, well, not 2.04 because that actually came from the solution here, but your total momentum does need to be positive. So this is not a solution. Okay, so then we can go back and equation 1 is still the same, so I can set equation 1 equal to my new equation 2, and that would give me 3 times the energy minus 0.511. That would have to be equal to the square root of this. What is that supposed to be? That's supposed to be squared. Oh, Okay, so this is 0.511 squared. So then we would solve this equation, but this gives two complex solutions, but those are not valid solutions. So it turns out that this is the only valid solution and we're good. So just to check to make sure that this doesn't work, you could plug it into your calculator or the computer, and because the only solutions are complex solutions, we can't have a complex value for the total energy. So we just have the one solution there. And that concludes problem 36.